let's just get started with a quick round of introductions. So I guess I'll start. I'm David Gleich. I'm a professor of computer science, or associate professor of computer science at Purdue University. And I do a lot of fun stuff with graphs and matrices and all sorts of other fun data objects. And I guess we're going to talk about some code that some of the other people will introduce themselves on and explain themselves as the author of the code. And I want to learn about this code, so that's why I'm here.
So I'll introduce myself next. I'm Anna Gilbert. I'm a professor of mathematics and statistics and data science at Yale University, and I'm interested in algorithms, huge data sets, and the interplay of mathematics and geometry and algorithms.
I can go. So I'm Nate Velt. I'm a postdoc over at Cornell University. Last year, I defended my PhD under David at Purdue University. And so he's the one that introduced me to the world of graphs and matrices and all the like.
Hi, so I'm Rishi. I'm a student, at University of Michigan. I'm going to graduate in a year, and I'm sort of interested in machine learning, math, and like algorithms and that sort of stuff.
All right, fantastic. I think the first thing maybe it'd be useful to at least explain in the recording is what we're going to be talking about and why it's sort of interesting to the various groups here. So I'll start by giving a little bit of context to why I'm interested in it. One of the things that we end up doing a lot with graphs and networks and everything else is clustering them. And one of the things about clustering that you always have to do is you generally have to pick some parameters of your clustering algorithm. And one of the most common parameters you tend to have to pick is the number of clusters. And so if you've ever done k-means clustering or anything like that, you got to pick this number of clusters and then go on from there. And the algorithm then tends to search. I mean, then there's usually some strategy of how did you pick that number of clusters? Well, so there's a totally different clustering strategy out there called correlation clustering, where what you basically provide as input is some measure of how much data points want to be clustered together and some measure of how much data points want to be clustered in different clusters. And then the cool thing about correlation clustering is that it sets up a problem that automatically determines the number of clusters. So it's got this different flavor than some of the other algorithms out there in terms of you don't need to specify the number of clusters as an input to it. You specify these sort of affinities or dissimilarities. And so at some point in my life, I was going to visit Australia. And as part of that, I spent a couple of weeks working with Tony Worth down there on correlation clustering things. And we developed a few different ideas that then led into a paper with Nate on some low rank correlation clustering ideas. And then correlation clustering is one of these very well-studied problems from an algorithmic perspective, because it enables you to do a lot of nice stuff with approximation algorithms. And so as you set up a correlation clustering problem, it tends to be NP hard, and so then you want to get some type of bounded approximation. And so there's an extensive literature that at the moment I know Nate is up to speed up on most of them, because he just looked at most of this last year as part of his PhD, and he would remind me of all the mistakes I make. But a large class of techniques involving solving correlation clustering correlation clusterings via these approximation algorithms start by taking correlation clustering and turning it into a linear program that needs to satisfy metric constraints. These are tractable optimization problems. However, they are extremely large and really difficult to solve in practice, such that I know your paper, or some of the stuff in your paper and some of the stuff in our stuff looks at how you would do these for correlation clustering on sort of off-the-shelf material, and you can solve, problems with 100 points or maybe a few thousand. I don't even think you can get to a few thousand points, whereas I know Anna's interested in big data. I'm also interested in big data, and there's always this question of what is big data, but I can tell you most people don't think 1,000 points is big data. There might be some debate about that threshold, but 1,000 points is on the, if it's big data, it's on the very small end of big data. And I think most people would say big data sort of starts at 1 million points. So then story continues for one particular, so Nate and I looked at some stuff for solving this that then led into a paper that I associate with Joel Trop for whatever reason, but now, Anna, was Joel your student or your postdoc? I can never remember.
Both.
And so there were some initial ideas on how you might solve these sort of metric constrained LPs. And so we took those and they enable us to get sort of a leg up on scalability on solving these things. And so Nate and I and Tony Worth and James Sanderson have a paper on that. And then we wanted to see how far it could go. And so we tried all the parallel tricks that we know of in order to make these things go a little bit faster. And you can get another little bit faster. And then you guys came along with another paper recently that actually goes quite a bit faster than our stuff. And so I am eager to hear about what sort of makes it tick. And so you also come at these problems from a very different perspective, which is more on the metric side versus the sort of approximation algorithm side, which is a nice counterpoint as well. So,
okay, so I'll do a little bit and explain where Rishi came into this. So I spent 10-15 years of my life working on like sparse approximations, sparse signal recovery algorithms. And at some point I thought, in all of the excitement in this area, I bet there was some work that happened like just as that wave started to pick up, that some of that work that kind of got a little lost. And what if I go and revisit some of these older papers, knowing, sort of what had happened in the last 10 or 15 years. And the paper that I went to look at was Joel Trop's metric nearness paper. And I realized they were essentially asking for, sort of the best repair to a broken metric best in some L2 sense, which is like saying, I want to find a good representation to my data, but in an L2 sense, like not taking into account sparsity or anything like that. And I thought, oh, this is a fantastic question if I just change the 2 to a 0. And in fact, it looks an awful lot like a bunch of the problems that our community has been working on for 10 or 15 years, but in fact, it's completely different. And I also thought it was a more natural question to ask, like, what is the fewest number of distances I need to change in order to ensure that I have a metric? That seemed like an incredibly natural question, and it just astonished me that nobody asked it. And so I worked with a postdoc. He's now Lalit Jain. He's now a faculty member at the University of Washington. And we came up with some hacks, some heuristics, something provable. And I knew that it was a really interesting problem. What we did was just purely combinatorial. I knew that there was a really interesting area, and sort of the combination of metric problems, combinatorial algorithmic ways of looking at things, not purely optimization, was really interesting. And Rishi came to me and he said, I'm interested in working with you. And I said, well, that's great. I know that you have a background both in computer science and in math, and you know a lot about extremal combinatorics and much more than one might think of an applied math graduate student. And I have this fantastic problem area for you. And Rishi, would generated like 5 ideas a month. We wrote several papers in sort of this metric repair idea. And then finally he said, I think I have a good, like, big picture way of viewing these problems. We are solving we are solving optimization problems with metric constraints. And I know how to solve this in a big way. I was like, oh, okay, this is great. So I think this is where Rishi comes in.
Yeah, so I looked at that paper by Joel and everyone, and they said they used this idea called Bregman iterations, and I was like, they didn't have much, so I sort of went into, like, I found the references, I read the proofs, and I was like, wait, this can be improved, and which is basically sort of what the basis for our paper is. So it started off with trying to solve these metric constraint problems, and then became more of like, how do I improve this optimization method? But still very much focused on like metric constraint problems.
Topic. So let's dive into your paper and code. Okay. So the paper is called Project and Forget. So it's one of these papers that has a nice catchy title too. So that's even better. And do you just want to walk us through sort of in the paper, the sort of like really big framework so this is a paper that sort of sets up a big framework and then specializes it to different problems, right? Okay. Do you want to briefly set up the overall framework, and then we can look at sort of, I guess I'm most interested in the correlation clustering part, but you know, we should probably give your brilliant work all the due diligence it merits.
Okay. So as you can see, even here in our problem definition, we've set it up mostly for the metric constraint version.
Okay.
But the general idea was, let's say you have a convex function f, and well, we have some assumptions on this function. Specifically, we will assume that Bregman function, which involves mostly sort of strict convexity, continuity of the partial, and like a couple of other properties. And
again, I'm going to ask lots of simple questions as we go along. So a Bregman function versus a convex function. So there's convex, there's strongly convex. Where does Bregman, like a Bregman convex function, or would you call it Bregman convex, or would you?
So it's just Bregman function. So it's a strictly convex function. Firstly, it's not convex and it's not strongly convex. You just need sort of strict convexity.
Okay.
And so, like I said, it's continuous, it's strictly convex, and has this sort of partial derivatives are continuous.
Okay.
And then it has
can you remind me of the difference between strictly and strongly convex?
So strictly convex, in some sense, if you look at the one-dimensional case, is that line joining any 2 points lies strictly above the function.
Okay.
Strongly convex is that your Hessian is always positive definite.
Okay.
Which is...
So for a one-dimensional function, are these two equivalent, or are there one-dimensional functions that...
I'm not sure.
Okay. Well, I'm not sure.
I know in higher dimensions they're not equivalent.
So I guess I would have thought that the absolute value function doesn't have second derivatives. It doesn't even have a first derivative at 0.
It was also not strictly convex, right?
Because you have, like, if you're on that line, right?
Oh, right. Okay, got it. Yes, sorry, I was putting the line somewhere else. Okay, good. Not a good example.
These might be equivalent for one-dimensional.
Okay.
I can't, off the top of my head, I don't have a counter.
Okay, got it. Yeah.
And then you have these sort of other definitions that have to do with this thing called the Bregman distance and how they relate to that sort of function. And these are sort of, as you can see, a lot more technical.
So a lot of times with these technical assumptions, there's some sort of edge case that you're trying to protect against. Is there any intuition for what that edge case is?
So from what I understand is basically, so let me scroll up. The definition of Bregman distance. Right, so the Bregman distance is defined as this sort of stuff. And the edge case they seem to be protecting against is like, oh, look, if you take sequences and they converge in your normal metric sense, you still want them to converge under this distance function.
Okay.
It's basically what those technical assumptions are saying.
Okay, so it's basically sequences behave like we would want them to. And so, all right. And now I guess I'll ask an annoying question, which is that a lot of times these technical conditions are sort of computationally uncheckable. I mean, I think you can prove for certain things that they satisfy them, but if you were to be given access to a function, could you actually verify these technical conditions?
I don't know about computationally, but theoretically they seem to be not too bad. And a lot of functions, a lot of common functions are Bregman functions. So for example, in one dimension, your quadratic function is Bregman, your exponential function is Bregman, the entropy function is Bregman. If you have a Bregman function in each coordinate and you sum them up, that gives you a Bregman function on multi-dimensional space. So,
awesome. Are there compositions that people always want to work, but that don't work for Bregman functions?
So the L1 norm is not Bregman because it's not strictly convex.
Yeah. Okay. All right. So we've got a Bregman function f, and we are trying to minimize that Bregman function subject to a nice set of linear constraints. So ax is less than or equal to b. And then x is also a metric on G. And so G here is a graph, or what is...
Right, so let's ignore that part for now. Let's just say you have some Bregman function that you want to minimize subject to a whole bunch of linear constraints, and you have just a large number of linear constraints.
Okay, all right.
So that's just the global big picture setup. The whole metric stuff is more specific. And our point is, we say this matrix A is like extremely large. In the case of metric constraint problems, it's like n cubed. Some other problems, maybe even exponential, and we just don't want to write it down. And so what our algorithm needs is this, it needs an oracle that sort of takes a point X and gives us some sort of violated constraints. And we sort of look at this in terms of two different oracles. So the first one is the sort of deterministic oracle, which we have a whole bunch of constraints, which are denoted by this family H. This Q has to run in polynomial time. And
so can I ask about that? Is it, I mean, if you want to state something about the runtime, it's going to have to run in polynomial time, but do you really just mean fast?
Yes.
Okay.
So the faster the oracle, the better.
Okay. I mean, and the reason I ask that is there's all this stuff that people are doing empirically with clique. And now clique is officially not something that runs in polynomial time, but if you have a real world data graph, apparently these things look nothing like the worst case problems or like the worst case instances for clique enumeration or clique or for finding the maximum clique. And so you can run these things quite effectively, even though in theory, this is an exponential time thing. Okay, so Q has to run fast and formally polynomial time, but fast would be good enough in practice.
I think Anna had a comment.
Yeah, I was just going to say, when Rishi was describing the constraints, you know, you've got first of all, X has to be a metric. It's got to be in the metric polytope, and then you could have additional constraints. This matrix A captures additional constraints like you find in correlation clustering. But also Rishi has a really nice geometric way of describing these inequality constraints as, you know, coming from half space constraints. And so he's got an even more general way of thinking about this. You know, suppose your constraints are all just, you know, intersections of a whole bunch of half spaces. And the setup for the oracle is in terms of, you know, you've got to, you a deterministic polynomial time deterministic separation oracle for a whole bunch of half spaces.
Okay.
That's the
Okay, so
full
you need to decide amongst this. So the idea is show me what's violated amongst any size set of constraints you want. You just need to be able to tell me those quickly.
Right, so we don't need to find all that's violated. We don't need to find the thing that's violated the most. We just want there to be some sort of like non-decreasing continuous function that's of the most violated constraint or something. And we want our oracle.
You don't actually need to have all of them. You just need some of them, or.
Yeah, so the oracle doesn't actually need to return all the violated constraints. It needs to return some of them. And the violations of these constraints need to meet some sort of like minimum threshold of like how good they are.
But
and if you did require,
oh, sorry, go ahead, Nate.
I was just going to say, if you did require to return all of the constraints, then you would no longer necessarily have things being polynomial time, right? Because your constraints, it could be exponential. So is it possible for, like, for example, there could be an exponential number of violated constraints. And so having to return all of them ruins your polynomial runtime right off the bat.
Yes.
Okay.
Yeah, so I guess this inequality 3.1 says, you know, you're going to return a list of violated constraints, you know, such that they're all like greater than some minimum distance.
Okay.
You don't even want all. You just want the maximum in
Oh,
that
okay.
list.
Okay.
Right, to be greater than some minimum distance to your polytope.
Ah, okay.
Okay. And do you have to see, I mean, presumably eventually if there's a violated constraint, you would need your algorithm to catch it, right? So is that distance threshold going to be decreasing as you run this more and more, or are you going to drive that down? Okay.
Right, so that's what it has to do with this sort of like thing about the function.
Okay. Got it. Cool.
Okay. Right. So we sort of access either to that, or we have another one.
Sorry, since this is an interview, I kind of want to ask if there's anything else you considered in terms of what you were looking at there that didn't end up working, or something you like, you know, when you're doing these things, oftentimes you have other ideas that you explore and never get to write about or anything like that.
So yes, I considered like just not having this function, like it just returns some violated constraint, and I was hoped that would be good enough. But like going to sort of the convergence didn't work out. Okay. You would sort of get stuck where you keep making improvements, but like your improvements are not enough. Okay. To get you into sort of the thing. And so hence you need the sort of bound to say, well, we're improving and we're improving at like a minimum enough rate that we will get there. Okay. Sort of thing. And so we mostly use this, but just for interest, since people do a lot of randomized algorithms. If you also have an oracle that just randomly returns a whole bunch of constraints, and your distribution by which you return them is such that every constraint is returned with probability at least tau, then the whole procedure still works. Okay. Huh.
So what would be an instance where you have a randomized checker that would be sort of faster or better than the deterministic one?
So the one, at least in the paper where we use a randomized one, is we use this to sort of train L2 SVMs when you have millions of data points. Okay. And in this case, not all the constraints are meaningful, just some random subset is similar to like the whole thing. So just randomly picking them seems to work well.
Okay. Got it. Cool.
Okay. So yeah, that was the oracle. Right, so we have this problem that we want to solve, and the basic algorithm is, well, you use your oracle, here we say metric violation for the metric constraints, to return some list of violated constraints. You have a list that you already sort of maintained from previous iterations. Just merge them. What you do is you do these Bregman projections onto each hyperplane in this list. And then the final step, which sort of helps us speed up, is you forget some constraints.
Okay.
And we have a whole bunch, we have some conditions on what constraints you can forget and when.
So what's the intuition with forgetting the constraints? I mean, I understand the computational one, which is to get rid of irrelevant stuff, but is there are there other intuitions there?
So you're forgetting inactive constraints is basically what's happening. And what you're left with at the end is active constraints are the ones that you will remember, and inactive constraints are the ones you will forget.
Okay.
So in a lot of these problems, you might have like n cubed total constraints, but your active constraints are more like n or n squared, which is a big difference.
Okay. So I guess, and then the set Z, like the variable Z, are those something like dual variables, or is that, okay.
Yep, so Z is a dual variable.
All right, got it. Now, taking a step back, I think Anna briefly alluded to this, but when, like, if you had asked me how you would set up the metric constraints, I would have said, well, we need to satisfy these n cubed triangle inequality constraints. But those aren't what you're using as far as the constraints for the metric violations, are they?
No, so what we're using is, so we actually generalize a triangle inequality to what we call cycle inequalities.
Okay.
Where instead of having, say, the distance between 2 points is smaller than the distance, say, from distance between x and y is smaller than distance from x to z plus z to y. We say the cycle inequality is distance from x to y is smaller than, say, x to z1, z1 to z2, z2 to z3, and so on, and then the last point to y.
Okay.
And so for each sort of cycle in your graph, we get a inequality.
Okay.
And each of these inequalities must be satisfied.
Okay.
So one particular thing is if you have a graph G, just in general, that's not a complete graph, satisfying all of these cycle inequalities and making sure your distances are positive is enough to say that these distances are actually come from a metric.
Okay. So in some sense, you're making the problem like a heck of a lot harder by introducing lots more constraints that just sort of, and now the reason to do that is that the oracle is cheaper, or is the oracle more effective, or to put this a different way, if you would run your algorithm instead with the triangle violations, would it work as well, or?
So there are two things. One, we can now solve, I guess, slightly different, bigger class of problems, where you only want to learn a metric on a graph instead of a metric on like everything. Okay. And
so this is where you sort of and when you say a metric on a graph versus a metric on everything, I think I'm a matrix person at heart, and so I guess I would, like, is it equivalent to think I've just got a matrix and I'm specifying a sparsity pattern of that matrix, and what I want to do, and yes, it's got to be symmetric for people who want to get overly general or something like that, but I've got a symmetric sparsity pattern, and then I want to learn the associated weights. That's what you mean by a more general metric, right? Okay. And what Nate and I are interested in the correlation clustering case, you don't have that prescribed sparsity pattern. You just want to learn fit the metric over all of the available and choose 2 elements or whatever it is. Okay.
Right. So I think one way to answer your question, David, is to say, when you have the complete graph, cycles are triangles.
Okay.
But
there are other cycles too. I mean, you can go further if you want to.
Well, I mean, let's just restrict ourselves to triangles for the complete graph. But you could do something much more general, and not have a complete graph, which is to say like a certain, a specific sparsity pattern in your adjacency
Mm-hmm.
matrix,
Mm-hmm.
instead of it being full.
Mm-hmm.
And you could say, instead of just doing triangles, I could imagine that I don't actually have triangles, but I do have longer cycles.
Okay.
And what's the more general thing to do? But yes, you could instantiate all of Rishi's stuff on a complete graph and just look at triangles.
Okay.
Right. Like I said, so the oracle and the forgetting step are sort of general with like some conditions on them, but we have specific ones that we like using.
Okay.
So the other thing specifically with the metric constraint problem is if you're solving, so the way the oracle works is what it does is it computes the all pair shortest path metric on our given graph. So if it's a complete graph, this thing runs in like cubic time.
Okay.
They use the Bellman-Ford algorithm or something like that. However, if you have a sparse graph, you could use Dijkstra's algorithm sort of on each node.
Mm-hmm.
And now you run in like n squared log n plus like n times number of edges.
Mm-hmm.
And if your number of edges is subcubic, you're now running in a subcubic time. So you find constraints faster.
Okay. Okay. All right. I think I've got the general setup. Do we want to dive into code, or do we want to, I guess one last question, and this is sort of for Nate. Nate, I know in a lot of the correlation clustering literature, there are relationships between these longer cycles, like the cycles with a negative edge, and some of the approximation ratios. Is there anything interesting in how metrics are treated there, or anything that we said that sort of caused you to think of something in that space?
So we've actually used a couple of these results in some of our papers. Like if you think of, I think we've cited Tony Wirth's thesis twice, where he has this alternate way to write the correlation clustering LP. And I'm pretty sure it's equivalent, although it depends a little bit on what you mean by cycle and what you count as an edge, because in some of those results, it depends a little, like a cycle is a cycle of positive edges and then one negative edge at the end in some cases, I believe. And so in that sense, I'm not entirely sure if everything is exactly the same. I think on some level, though, this is the same observation that Tony made about a different way to write the correlation clustering LP relaxation, where you can write it out in terms of an exponential number of constraints, but then you can solve an all pairs shortest paths essentially, so that you're not actually in practice working with the full exponential constraint set. And so I'm pretty sure underneath it all, this is all the same stuff that some people in the correlation clustering literature have made a few comments about.
Okay. All right, well, let's dig into the code because I want to kind of see how this works. Jupyter Notebook looks like Julia 1.1. All right, good. I love Julia, so hopefully you don't hate it after using it for this particular project. But
I don't know. I use Julia for most of my.
We'll have to have a different discussion, or maybe at the end of this on a Julia converts thing, and we can talk about what we love and hate about it. Or sorry, what we love and what ought to be improved. Our 5-year-old and their daycare got upset with the word hate. When, it is a pretty, it's a pretty brittle word. And so he's always encouraged us to use more descriptive vocabulary. And so I always try that all the time now. And so, okay, so you call this Bregman CC, and the inputs are, so Bregman is Bregman is the Bregman sort of framework, and then CC is correlation clustering.
Yep.
And so the inputs are D, which is, what is D here?
So D would be, I guess, our metric.
Okay.
So maybe it might be useful to go back to the paper for a second and look at the actual formulation of the problem we're solving.
Okay.
Right. So I guess from your paper is what we got. This is the version, like the QP that we solved.
All right. Got it. Okay.
Right. So here D is sort of your metric, and then W is this like positive definite matrix. You compute it like
Okay.
normalize this quadratic term.
Okay. And W, if I'm not mistaken, was that one the diagonal term? So it's a diagonal matrix W, or was that a different?
So I guess in this formulation, yeah, it's a diagonal matrix. So where's the code? Right, so it takes in D, and well, the code doesn't really need W. It needs W inverse for everything.
Okay.
So it has that. It takes in C. C is sort of like, if you expand this out and write it as like a linear program, C is a linear term.
Okay.
Gamma is, well, gamma over here. And
So,
your tolerance is like how far do you want it to converge?
Okay. And so when I think of a correlation clustering problem, I generally like to think of the input as being this matrix of positive and negative weights. Nate or Rishi, do you want to remind us how you sort of convert from that into the D and the W inverse?
So I actually just use your code.
There we go.
It's just here.
Okay, so
that computes these sort of things.
Okay.
So in that case, D is just ones and zeros, if I remember correctly, right? So it's a 1 if there's a positive edge, a 0 if there's a negative edge, and then every edge has a weight, and that weight is in your matrix W.
Okay.
Yes.
Awesome. Okay.
Right. You're not mentioning the fact that that we came down to Purdue and spent a while talking to you guys.
Yes, that's true.
We did do that, yeah.
we went
so it sounds like you had all of this figured out before you talked to us, though, because your questions were, I mean, at least a large portion of this framework you seem to have sort of realized already.
So as I recall, we sort of came with a hammer and we were looking for various nails, and we wanted to know how our hammer compared to other people's hammers, and we wanted to know the right way to do the comparisons.
Okay. Yes, that's right. Yeah. And so we told them about. We told you about our hammer, and I was sort of excited when I heard about yours, because again, the nice thing about yours is that it involves a lot of shortest path computations, which are a lot easier to deal with than whatever the heck we were doing with trying to find like parallel colorings of this basically you look for sets of constraints that you can update independently in this in this other algorithm, and you sort of end up with some fundamental limits to how fast you might be able to go there. And so I was very excited when I heard about the possibility of doing things with shortest paths instead.
So I don't know if this is the place to ask the question, but down the road, I'm going to be asking how you both work on the sparse problems. Because as I said, this D matrix is ones and zeros if there's a positive edge or a negative edge. And one sort of assumption, in many cases, a limitation of our framework is we assume a dense graph, where dense means there's either a positive edge or a negative edge. That's why there's either a 1 or a 0 in the D matrix. And so one thing I'm particularly excited about, hopefully hearing more about today, is how actually you free yourself from thinking about things that way to solve these much larger, or larger in terms of nodes, but sparse problems that I don't think our code has any hope of solving. So the answer might come later, but that's what I'm looking forward to hearing more about too.
Okay.
Right, so we sort of get these inputs. G here, I'm just making sort of a complete graph, just an object. Z here is our dictionary of dual variables. I'm not going to store it as like a matrix or something dense, because I don't, in the end, we're going to have a few of these. Since we also solve the L1 stuff, there's also this whole bunch of stuff about how you make sure your variables are the absolute value of something, and there's a standard trick, and so these are the variables sort of related to that.
Okay.
And then f is, I guess, the variable we want to learn, and we initialize it to, I guess, the stationary point of our objective function. Right? Because if you think about w as the quadratic part, c is the linear part, solve for the 0.
Okay.
Okay. So then the first thing we do is, well, we call the Floyd-Warshall algorithm on like our instance, right? Our graph and our weights, it returns this Floyd-Warshall object. We extract the distances, and then B, we also extract sort of the shortest paths.
Okay.
Is this shortest path in terms of just positive edges?
So this is in terms of D. So D will be the metric, right? So the weights are 1s and 0.
Mm-hmm. So it's shortest path in terms of just the ones.
So your edge weights also have 0. So it could find like a path with all zeros.
Okay.
Right.
In fact, it will try and include as many zeros as possible, right?
Yep.
So Nate, the zeros are the negative edges or the?
I think I said that before, but now I'm thinking it's opposite. The zeros are the positive edges. Okay. Because as distance, you want to be distance 0, and you want to be distance 0 from things that you have a positive edge with.
Okay, got it.
Okay. Right, so we sort of just compute these objects. Again, these are sort of just metrics to see whether you converge, not converge, how far we are. And in particular, this is your distances, and this is your weights. And this I'm just looking at sort of what the L1 difference is between that.
Okay.
And so then what I do is I go to each edge, and I check whether the weight of that edge is bigger than the weight of the shortest path.
Okay.
Right, because if the weight of the edge is bigger than the weight of the shortest path, you found some sort of violated constraint.
Mm-hmm.
Right, and then you have all of this code to like compute the Bregman projection.
Okay.
So I guess the first few lines, just these are sort of extracting the path. Right, so this B is just that path, length, my first node, my last node, up until here. I am doing the projection.
Okay.
That's sort of the Bregman projection.
Why doesn't that end? So sorry, you enumerate over the length of the path with K there, and then you compute something with M and D, and then what? So if D is small, what does D represent?
So D is sort of the violation of the constraint. So if it's negative, you violated the constraint. This is a little bit ad hoc because sort of I found it over here. I computed these U's, but I am changing the weights before I could get to like all the edges.
Oh, so you're updating the weights as you go along, and so it's a So
I could have fixed something that was broken before.
Yeah.
This is not part of the this is sort of like engineering or like part of the code.
Well, no, that's the good stuff to go over because these are the questions that always come up when you go through the difference between the paper and the code. It's like, wait a second, why did you choose to do it that way? So in some problems, you have a choice between sort of computing all the updates you would have done under the current information and then applying them in bulk versus computing an update, immediately updating that, and then recomputing the next one as you go along. So in this one, you're doing the latter.
In the sparse
presumably because
version,
it's faster, or is there?
Yeah, it seemed to be faster. In the sparse version, I actually do the opposite, where sort of like once I compute everything, I just like add all the things and then do the update somewhere else. Right, so then here I check whether it's still violated. Then I guess this is the projection. And then this is the forget step. So the forget step is basically got to do with, so like I said, you forget inactive constraints. So from like Lagrange duality, your constraint is inactive if your dual variable is 0. Right? And so basically, if like you do something like this where your dual variable becomes 0, I don't actually forget them here. That's something I noticed. Let's just say this is currently, at least over here, this is just updating the dual variables. I'm not actually doing the forget part over here.
Okay.
All right, and then sort of I'm updating this like maximum violate constraint sort of thing.
Mm-hmm.
And that was sort of an initial loop, and then
Okay.
I sort of like call this loop function that continues it.
So that was an initial sort of hot start, warm up. Yeah.
Yep. So what the loop function does is, the first thing it does is so I go to my list of violated constraints twice.
Okay.
That's just
why twice? You'll explain why twice.
Yep.
Okay.
So basically, let's just look at it for the first time, right? So I look at each
Okay.
constraint for in my list Z. I again extract the path up till here. I do the projection up until here. And then here, when I'm updating dual variable,
Okay.
notice when Z is equal to C, right? Since I do Z minus C, it will be set to 0. So in this case, I can just delete the constraint.
Okay.
Because it's now become 0, and in my current sort of formulation, we think it's inactive. So we can just sort of delete it, and we do. And so the reason I do it twice is because we could have found a large number of constraints the first time.
Okay.
And we sort of go through this, and we see that a lot of these actually are like, there's a lot of dependencies here and redundancy. And so sort of fixing one fixed a whole bunch of other ones. And so you could delete a whole bunch.
Okay.
And so then I do it again to sort of like get that speed up.
So in some sense, the first pass is where you patch up the variables, and the second pass is where you really get rid of the redundant constraints.
Yeah. Or this could have been bigger. For the sparse version, this is actually 75.
Huh. Okay. Now a couple of quick questions here. My original training was all in numerical analysis, and so when I say if Z, like when I see stuff that says if Z is equal to C, that always sends warning signals up as far as do you expect exact equality there, or
no, I think I do have versions of the code where like this one here.
Okay.
Where
it's just version. If it's smaller than
Okay. I also have newer versions of the code where instead of like computing Z, so Z is actually the value of the dual variable over here, and I compute some C over here. So I just check, so C is equal to Z if it's Z is smaller than this number.
Okay.
So I think my more modern version code just says if Z is smaller than this.
Okay, got it. And which is much better behaved, yeah.
So where was? Right, so we're here.
Okay.
Was there other?
Nope. Well, I guess the other sort of silly question is, how are you storing paths in your Z dictionary? Is this just like a list, or is this?
So Z. So yeah. So P. The keys are a list.
Okay.
So you can see I do length of P, right? And then P at I plus 1. There's just a sequence of nodes.
Okay.
Okay. And then sort of here, H1, what it does over here is it makes sure all the variables are positive, or I think it might also make sure they're within positive and less than 1.
Okay.
Nope, in that case it's just...
That's sort of making sure that things are between 0 and 1, is the H1, or?
So yes. So I think that one's checking, I think that one's just making sure everything is bigger than 0.
Okay.
That's so that's one of the things you have to be careful about, is because your Floyd-Warshall will not work if you start having negative edge weight.
Yes.
It'll just sort of cycle forever, and these are issues that I ran into. Since you know that your final answers are positive, you can like add, just to make sure this E, which is the difference between like the weights that we're currently using and like our original weights, right? Basically this.
Okay. And you've got some long comment here on something that should cancel out but doesn't, or what's the?
Oh, I think this shouldn't be. This should be a you wouldn't.
Okay.
So basically, when I wrote the code, I was like, wait, I need to like account for this.
Okay.
When I do the projections, but then if you do the math, it all sort of like disappears. And this is just here to remind me that, oh, I did the math and like, I'm not just forgetting something.
Okay.
When I write my code.
This is always good practice to, at the very minimum, write comments for yourself, because if there's something clever in the code, you will forget it when you come back to it. And I can't tell you how many times that has happened to me. I'm sure it's happened to you too. There's all sorts of memorable experiences where it's like, wait, why? Yeah, so this is a great example of that. Okay. All right, so at a very high level, this then ends up being pretty, I mean, I don't want to say simple, I want to say straightforward, I think is the better way of doing it. You use basically Floyd-Warshall or whatever shortest path algorithm you want in order to find these these violated constraints. And then you just update variables in light of adjustments to them. And the updates, you know, are a little intricate to work out, or I think fussy might be the term I would use. So one question for you is how fussy are some of these updates? Because I know there's things like PDEs where if you squint at them wrong, you never get convergence and all of your nice formulations explode off to infinity in like no time at all. And there's other things like stochastic gradient descent where you can basically, you know, implement the algorithm completely incorrectly and it will still converge under all sorts of different scenarios.
I think it's closer to the stochastic gradient descent
Okay.
version. So at least numerically, as you can see, sort of, we're just multiplying or adding. So there's no weird issue where like you're dividing by some really small number, so it blows up.
Okay.
Unless, of course, I guess W has really large numbers, which I think is unlikely. And in most cases, sort of computing this projection, even if you're slightly off, tends to be all right.
Okay. That augurs well for all sorts of different scenarios, especially in floating point.
Yes, and like I said, I have this tolerance over here where I forget. I've made this like smaller, like that, and it still sort of converges. And it's not exactly this exact optimal, but it's close.
Okay. Okay. Let's see. And you had this other function, the enumerate paths to P. What that one was where you actually extract out the shortest paths?
Yeah, so that one basically what it does. So there's an enumerate paths that like does it in this library that I'm using, light graphs.
Light graphs.
But it's not parallel, or at least when I was doing it, it wasn't parallel. So I was just like parallelizing that.
Okay, and so you're enumerating over all vertices there, or what is?
Yeah, so all vertices. So I'm finding the shortest path. So basically, enumerate paths takes this, if I remember correctly, it takes this source and, or no, one of these, S is this object you got in.
Yeah. Okay. So this just goes from Floyd-Warshall output to actual like lists of vertices in the paths. Okay. And then where was the code that does the actual checking of all the different constraints to find the violated stuff? That would be loop. Is that where it is?
So there's that where you sort of start up once and then loop.
Yeah, you start up. Okay.
And then here, right? So I
Okay.
go to all the edges, like, well, I guess once I do the
Find the
float
new
more
broken.
shell.
Okay, so there it is. Got it. All right. Okay. I mean, there's obviously a lot to digest here, but okay. So I'll ask this: can we see it run on a small problem just to see what it does?
Sure. So here I have the setup.
Okay.
So this is, I guess, a small blog graph. So I did run it, and it took about 20 minutes still. So I want to like go through a little bit of the output before we run it again.
And how big is poll blog? It's like 1,000 or something like that.
I think so. Okay. So one of the things that I want to point out about this thing is given by these two graphs. So this blue line here is sort of like the number of constraints found by the oracle.
Okay.
And this red line is the number of constraints you have left after you do sort of the forget step.
Okay.
And as you can see, initially there was a huge difference between these.
Okay.
And it takes a while, but eventually sort of they converge to like similar numbers.
Okay. Sorry, I'm having trouble reading the axes on my screen. Can you just at least mention sort of what roughly what the numbers are?
Can I not? Okay.
Or zoom in,
maybe.
So
on the left, the number of iterations. So on the number of constraints. So for the blue on the top, it's like 10 to the 8.
Okay.
And for the red on the bottom, it's 10 to the 5.
Okay.
So it's 3 orders of magnitude, at least for this one. And as sort of you go through, about sometime in the middle, around like the 15th iteration or something, they converge and to somewhere between like 10 to the 5.8 or something.
Okay.
And one interesting thing to note is it takes a while before it starts to drop. And if you plot for the same one, what sort of your maximum violated constraint is, this is again on a log-log plot or a log linear plot. At the very beginning, sort of where your number of constraints being found is not dropping, your violation is also not really dropping.
Okay.
And once this number of constraints being found drops to sort of where your active constraints are, your violation also then starts decreasing.
Okay. I mean, the intuition is sort of when you're far away from where you need to be, like you just spend all your time trying to get in the right space. So, yeah.
Yep. And so sort of when I run it over here, as you can see, this maximum violated constraint will stay at 1 for quite a bit.
Okay.
Before it starts dropping.
Okay. And so you're just getting the adjacency matrix, you're setting all the diagonals to 0, you're building this Wong CC setup, and then running it. Okay.
Yep. So what you can see is the first time it found like this maximum violated constraint, and this is that L1 error that I was looking at before. Like, so for sum of all the violated constraints, or in some sense. Just to get a better sense. And then this is the number of constraints returned, or the number of constraints that are present after each iteration.
Okay.
And just to show you like how it drops when you do projections, this is like what it is when you first start projecting. This is what it is when you second time start projecting. It actually doesn't print what it is after your second set of projections, in which case it would be smaller. And as you can see, it tends to have like a gap, and that gap slowly gets smaller.
Okay.
And this one actually, it takes a while before you start noticing. So you have decreases here. It starts off with like 1.4, 10 to the 6. It's still not still not decreasing a lot.
Yeah.
Like I said, it'll sort of stay plateau until these two numbers, or at least this number, is close to what the number of active constraints is.
Okay.
In this case, it actually is quite a bit. It turned out to be like 750,000. So
fantastic. Yeah. So that just so it's about 7 seconds an iteration, and most of that time, I imagine, is doing the shortest path computation.
So this this number, this time, I think is printing, it's only printing the shortest path time, I think.
Okay.
Or is my timing, oh no, the time is for the whole loop.
Okay.
Yeah, most of it is in doing this and then this.
Right. And this is running on your laptop or some server you have access to? Or?
So this is running on a server. It has 8 cores and 30 gigs of RAM.
Okay. All right.
So the parallel part, so it's running the Floyd Warshall in parallel on the 8 cores.
Okay, fantastic. Yeah. Yeah, that's one of the nice things about that algorithm is it's, actually there's even communication avoiding versions of it where they sort of like tile the data through memory in this like super optimized way. So you can get some pretty optimized Floyd Warshall results. All right, Nate, any other questions about this? This looks excellent. I mean, it maps nicely onto the paper, and I mean, it's good to hear. So I guess are there, you've mentioned a few little tricks in implementing this, like do the 2 iterations to sort of forget a few more things. Are there any other insights, I guess I would say, rather than tricks?
So you don't have to do 2, you could do like 5, 10, it doesn't really matter how many times you do it, the convergence results works out. And the reason why I would want to do it more times is sometimes computing the oracle is the most expensive part. And a lot of times you don't need to do it that often.
Okay.
I haven't done this and I don't have a good way of doing this, but as you can see, as we sort of go through, our oracle stops finding a lot of constraints. So some way to sort of balance not really calling the oracle that much. I had a version where the number of times you do the projections increases as your number of iterations goes on.
Okay, well, this looks fantastic. So Nate, you want to understand more about the sparse case now too, right?
That's what I'm most curious about. Yeah, that would be great.
Okay.
Okay, where is it? So this is what the problem sort of becomes when you have like the dense case. If you sort of do the same sort of reduction when you have the sparse version, your objective will not have any of the terms for the sparse distances that you don't have. All right, so in terms your D only has things to do with the edges you do have, and your W, if I remember correctly, said 0 for the edges you don't have. So what we basically do is instead of saying that X has to belong to this metric on like the complete graph, we say that X has to belong. So for example, just this thing is like if your function only depends on like the edges in your graph and you want to compute like your constraints are the metric in like on the complete graph, it's equivalent to just do it on like just that graph because your objective function doesn't depend on those other edges or those other weights. And there's some like geometry behind like why this and that polytope are basically the same. Yeah, so we just sort of have this instead.
So let me ask maybe a potentially silly question at this point. If you're looking at the theoretical algorithms for correlation clustering, you can run those on sparse networks as well. And the rounding usually assumes that you still have some xij for every pair of nodes i comma j. Now you can still do this sparsely. Can you still get some sort of a score between every pair of nodes? Or how would you handle that? Because if the rounding algorithm typically says, or typically assumes that I can get some sort of a score for how close I am to everything else when you're forming the clusters.
So once you have sort of just this X on the graph, you can extend it to like all the xij's using some
just by the shortest paths, essentially.
Floyd Warshall.
Good, that makes sense.
Because I'm not sure what those distances are if they're not part of your objective function anyway, and you just need them to like satisfy the metric constraints.
Okay.
So.
Cool. Yep, makes sense.
So then I guess, are there other big differences between the sparse case and the dense case? So you do it over this limited metric, or sorry, over this limited pattern. And you said you did 75 iterations of that forgetting step.
Yep.
I mean,
the only
I know 75 is a parameter that you can control, but
the reason I did 75 is because even though it's sparse, we're doing this for a lot bigger graphs. The sparse version, I think we did it for, yeah, those graphs.
Okay.
And so even though you're now all pair shortest path computation is subcubic, like at best, it's still quadratic.
Okay.
And quadratic is still bad.
Yeah.
Or it takes time on this, so I don't want to like do the all pair shortest path quite often.
Okay.
So
that's my wife talking behind me, so I might start muting.
Of multiple sublists, so you could take
Hold
one
on.
task.
Right, so this is why I do 75, because I don't want to call the oracle too often, and we do have, on the sparse one, there are fewer sort of constraints, and I think it's more likely that you find them quicker, so I do want to like project onto them more.
Let's see, do we have other stuff that we want to know about? I mean, this has been fantastic. I think this has given us a leg up on where to go. I mean, I guess the last thing that might be useful to discuss or just briefly brainstorm about is, are there places you think this could still be accelerated? Like, I mean, I don't want to like mine for your next research project or anything like that. That's not the intention of this question. But are there places where you see that there would be ways to speed this up that are potentially obvious or non-obvious or things like that?
So the major bottleneck is still the oracle computation. Though the projections still take some time, they're non-trivial. It's not like they happen instantaneously. There is a version of the Bregman projections where you do each projection in parallel, and then you average the projections.
So we had looked at that, Nate, right, for our stuff.
We had.
I'm not a related one.
I think so. The reason it did not work for us is because we are actually looking at the full cubic set, and since most of them are zero, you just get nowhere if you average stuff. Although in this situation, since you're looking at a much smaller set of constraints, I do wonder if that would maybe not average away to zero quite so poorly.
Right, so it shouldn't average to zero because you're only sort of doing for the violated ones, right, in some sense.
Right.
Right, so I tried proving a theory result, whether like this thing still converges if you do the sort of averaging and forgetting and introducing. And I thought about it for a little bit, and I think you could push the proof through, but I hadn't fully figured it out. I haven't tried implementing it, so I don't know whether it works in practice.
Okay.
So Nate had a question about this opt ratio, and I know that this is something, Rishi, that you and I discussed like maybe last week.
So I think this is again from sort of your paper where you're solving this QP instead of the LP for correlation clustering, and so you have a way of computing this opt ratio between the QP and the LP, I think.
Right.
Right. So
So all the theory goes through as well, because I mean I was focused.
Yep.
Okay. Yep. So that's the same thing.
Yep.
Right. So yeah, I was gonna say somebody was asking us about this, and it was creating somewhat of a mental block in this person's mind. Wait a minute, that's not very good. Well, no.
But I assume this is like with gamma equals 1 or something like that, which allows you to get some semi-reasonable convergence. And you still get.
I actually don't remember what gamma I set to.
Okay. Anyways.
It's probably says somewhere. But most likely it's gamma equal 1, I think.
Right. I found that the best response to that is, well, why, at least when you're thinking about solving correlation clustering problems, if you want to implement the theoretical algorithms are going to guarantee you an order log n approximation. And so why do you have to solve the LP? why not solve a QP if the QP is a lot easier to solve? And sure, a 1.7 approximation ratio doesn't look great, but like, why are we doing this in the first place?
Right.
Right. 1.7 log n is basically the same as 1 log n.
Right. And in practice, it's going to be better than that anyways. So.
Right. Are there other?
Well, that's it for stuff. You know, I think I wanted to learn about and chat about. Are there other things you would want people who are watching this video to potentially know? Like, I mean, we can always edit it later too, so it's not like this is.
So mostly we've been talking about correlation clustering, but the method can be used to do like other metric constraint problems. In particular, we look at metric nearness, which is the problem from Brickelt's paper, and there we did a more extensive comparison of these sort of off-the-shelf optimizers, and they don't do well. And even beyond metric constraint problems, we can also do just in general highly constrained optimization. And I think we have a recent paper with on optimal transport where you have quadratically many constraints instead of cubically many constraints, and we still sort of like outperform the standard like MOSAC, Cplex sort of type solvers.
So let me ask one other quick variation on this. I know in some variations of correlation clustering, you can sort of put in these like must link or cannot link constraints. So you basically fix various pieces of the solution a priori. I imagine it would be pretty easy to modify your code to put in some of those types of constraints.
Right, because those would just form as one of these sort of sets of linear inequality.
Do them there, or you're basically, I mean, if you're saying that they must be together, then you're kind of collapsing two nodes together, so the distance would be 0 between those nodes. So must link constraints would in some sense be easier.
Right, you can add the constraint that distance must be 0, and I guess in the code you can just add the projection, just like after everything, set this distance to 0.
Yeah.
Work out.
Okay. Nate, are there other very specialized inputs to correlation clustering that you remember that might be interesting?
I mean, I think in limited cases, some people care about putting a bound on clusters. I imagine theoretically that's something that you could do, but I don't think that's as common as must link or cannot link. Because then you're sort of ruining the thing that makes correlation clustering nice if you add a constraint that bounds the number of clusters.
Yes.
But in theory, I think that's something else you could add as a constraint.
Right, as long as you can add a sort of like linear constraints, you could just sort of like do those projections at the end of each iteration, and things will work out.
So looking prospectively a little bit more, the next thing people want to solve after they have some good techniques to solve something like LPs in this setting is they next want to solve SDPs, semi-definite programs. Is there some belief that some of these techniques might extend to solving semi-definite programs as well?
So yes, there is a version where instead of sort of like linear inequality constraints, you just have convex constraints.
Okay.
And we have the same sort of theory behind it.
Okay.
But now computing projections onto general convex constraints is not something you can do.
Yeah.
So in that case, that's the bottleneck there.
Okay.
So in particular, there are 3 steps, right? So we find violations, we do projections, and we forget. The forget step is always easy. There's no bottleneck, nothing there. So as we've been talking about, the oracle could have a bottleneck. The other one could be in actually computing the projections.
Okay.
So computing projections onto hyperplanes is easy for some classes of functions, specifically like the entropy, exponential. Even the exponential is pretty hard, actually, quadratic. However, if you go to, say, general convex functions and general convex constraints, computing this projection can be non-trivial. Though I imagine in SDPs, again, you have sort of quadratic functions and like very specific kinds of constraints. So you might be able to do the computation there.
Okay.
You know, very early on, we had some discussion about convex constraints and convex objective functions. And I can't remember if you did a simple example or not, but I do remember a very early version of this. We talked about that setup.
Right, so I have, so we have what you call the theory behind it. I don't have experiments.
Okay, right. It works in theory. We haven't tested it in practice.
Okay.
I remember we had this discussion. This was a long time ago, and we just sort of took it out and focused on you know, linear constraints. And
the algorithm is actually a little bit different there. But it had the same sort of idea, finding constraints, projections, and then forgetting constraints.
Okay. Now, if you'll indulge one more related question. So I don't mean to pry or snoop or anything like that, but it looks like the paper's been rejected a few times, or at least it shows up in open review, which I didn't look at where you tried to send it, but generally that.
Yeah, so we submitted it to IC, well, we submitted it in Europe last year, which it didn't get in. Then we submitted to ICLR, where it didn't get in. Then we submitted to ICML recently, where it had better reviews, but didn't get in. And now it's submitted to NeurIPS, where again we have better reviews, but there's still that one annoying reviewer.
Well, I'm sorry to say I've never had the opportunity to review this. I'm obviously a big fan. So yeah, I mean, for whatever reason, we had a lot of trouble with our parallel correlation clustering thing too. It seems like
we had trouble with the first one too, even before the parallel version.
Yeah, and so we sent the first one we sent to NeurIPS, and NeurIPS wanted nothing to do with that one, if I remember right. The reviews were were fairly negative, and then I think we just sent it to SciMods, right? Or did we send it somewhere else before then?
Right away to SciMods after that.
And then the next one we tried
TDPS.
Yes, transactions on distributing in parallel systems. They didn't like it. And then we tried VLDB and they didn't like it. And then we just sent it to this conference on combinatorial scientific computing, and they really liked it because it's more their kind of stuff. But yeah, I don't know, like there's unfortunately not necessarily great places to send a lot of these papers that sort of make, I think, solid technical progress on older problems that doesn't have a, like doesn't involve some flashy new technique, I guess. Even though I think a lot of this stuff is new. So I don't know.
So one thing about this process, I mean, it's frustrating. On the other hand, every time somebody asks us a question to poke at the paper, we do more experiments, and the evidence just keeps getting better and better.
Yeah.
So
the most recent time people asked us for more convergence details of these other solvers, and we have this sort of table which shows that they don't really converge as much as we do.
Okay.
Yeah. I mean, what can I say? You know, the reviewers are making us work more to show that the algorithm is actually better than we had thought. You know, our next step is to send this to a journal, though. It's the paper's not getting better. The experiments are getting better.
Yeah, I guess the thing that frustrates me with some of the feedback I get at conferences is it's good feedback, it's all correct, but it's not honest in the sense that even if I do everything that you say, you're still not going to say yes. Whereas the thing about journals is usually it goes back to the same referees. So it's not like you get another, like if I say address these things, then, you know, if you do that and it comes out even better, there's the sort of like, okay, well, the editor's not, I mean, if I then go back and say reject on the second time after you did all this work, the editor generally steps in and says like, okay. Yeah, no, I agree the feedback is often good. It's just that there's no, like the lack of memory ends up being you spend your time spinning in place. And so and I am,
there's no assumption that if you revise that you can resubmit and it will, and people will say, oh yes, you answered these questions. Great.
Yeah, exactly. No, they'll just come up with,
I mean, one of the things about this method is that it's incredibly general, and you know you can tweak it for various problems, and so you know Rishi's been adapting this framework. You know, it doesn't, you know, maybe even substantially changing it for other kinds of problems, and you know, hopefully those changes, well, they're definitely leading to more papers, and some of them actually get reviewed quite positively. So it's kind of like, okay, well, we've got the hammer, and you really like the hammer with the red handle on the green nails.
Yes, yes. That is how it feels sometimes.
So, well, that suggests that the hammer needs an archival toolbox for it to be put in, and for everybody to use this hammer, but to put their own handles on it. Rishi, your code is available.
Yeah. You go to GitHub. I think there's a repository called Project and Forget that has all of it.
All right, project and forget. Oh, fantastic. Okay. And yeah, you can clone it. And well, as I was saying, it was just a distinct pleasure to chat with you. I've certainly learned a lot, and this is, I don't know, I'm eager to dive into the code a little bit more. And so I don't know if I'll get to it soon, but I now have the recording that I can refer back to look at these things. So thank you for taking a few hours to chat with us.
If you have more questions, like feel free to send me an email. I could like try and figure out what's going on.